Examples part 2, day 94. You're given the expression where the Kb is equal to the hydroxide over CH4OH2 plus 1, and then over the methylamine. Part A says, write a chemical equation showing how the methylamine behaves as a base in water. So what you're to do from that is look at the expression and be able to interpret the data from that, or the equation. So how would I write that? How's the expression written? Products over reactants, right? Okay, yeah, that's a good idea. So we know that we have our reactant, which is CH4, the methylamine. And is this a weak acid or a weak base? It's a base because it says it's a base. And also you're given a Kb value, and it says it's a base. So we have to show water. And then from our expression, we have our hydroxide and our conjugate acid there, so CH4OH2 with a plus 1. Okay, so that's part A right there. And again, this is a past AP exam question from a while back, but I really like it because a lot of students, when they first see something like that, they're like, what do you do? Well, remember, the expression is always products over the reactants, and we never include water. And if it's a weak base, you have to show water. Part B, I left out a lot of room for that part, didn't I? Part B says calculate the pH of a 0.588 molar solution of the methylamine. So we have our ice chart already made. Isn't that cool? So part B, we know that we have 0.588. Do we know anything else about the others? No. So pretty straightforward. Okay. And then from the expression that was given, our Kv, we have them. And did you guys want to use 5% rule?
Yeah.
I love asking that question. And it's 4.57, that's given. Times 10 to the negative 5. So again, nothing new here, hopefully. Hopefully. .69 times 10 to the negative 5, and then x is equal to the square root of that. And what does x represent that we care about here? What is it? The hydroxide. Good. That's supposed to be an x. So calculating pH. Again, you can find the pOH, or, whoops, let's do 14, minus the negative log of the hydroxide. Get that better. 11.71. Okay. And is that answer reasonable? In other words, 11.71 for a base? Good.
No.
Okay. No?
Well, you're asking something. No.
So our pH, that's our start. Okay. All right. Let's scoot this over. Part C, whole different question, and then unfortunately it has nothing to do with equilibrium, has nothing to do with equilibrium or acids and bases, but it's a great concept question. It says write the net ionic equation for the reaction between the weak base and the strong acid. Now, I will admit that when we look at our weak base, this is, and nobody's an organic, right? I know I ask that every day. This is an organic compound, which is not ionic. Also, this will not break apart into ionic compounds or ions. However, this can be considered to be ionic once it has that charge. So even though, unfortunately, not everything is ionic in nature, it does have some ability to become ionic. So let's go ahead and write it. So it's going to react with the nitric acid. In other words, what we have, and I'm writing the equation before I write the ionic equation, before I write the net ionic equation, because back when we do a double replacement reaction, which this really isn't a double replacement reaction, but it's an acid with a base reaction. Good morning. Got the papers there. What's going to happen is we're going to rip a hydrogen off and place it on the base. So we'll have CH4OH2 with a +1 charge and then nitrate. Okay? So that's our reaction. And what does the nitrate do in solution? Nothing. It's a spectator. So this is our equation, the ionic equation, or somewhat ionic equation, I should say. Looks like this, where we have CH4OH plus, H plus, and nitrate. Okay? Because really, when we look at a strong acid in the container, that's what we have. We have hydrogen ions and nitrate ions. That's the reality. And when these guys react, we'll form this, which is CH4OH2 with a +1 charge and nitrate. This is the quote-unquote ionic equation. When you do a net ionic equation, does anybody remember who you do not include for net ionic? It's been a while.
Hydrogen.
Spectators, very good. Things that don't change. So if it looks the same on both sides, we don't include it. Okay? In other words, if I look at the nitrate and the nitrate, it's not doing anything. If I look at the methylamine, it has one more hydrogen. If I look at the hydrogen, it's now attached to the methylamine, forming the conjugate acid. So in the net ionic, if it looks the same on both sides, in other words, has the same chemical makeup, has the same charge, everything looks the same, don't include it in the net ionic equation. It actually goes back and forth. So if you want to write it with a single arrow or double arrow, you're not going to get beat up for that. Okay? So really what this is, it's the mechanism for what's happening. Now, you've already known about that. You're like, oh yeah, we always put hydrogen with the weak base to make the conjugate acid. We've been doing that for weeks, but we just haven't had a name to go along with it. Okay? All right, so that's C. Yeah, that's C. All right, I apologize. I didn't give you a whole lot of room in part D. All right, part D, similar to part C on last night's homework, says in an experiment, 42 milliliters of a 0.588 molar methylamine, or the weak base, is placed in a flask and titrated with 10 milliliters of our 0.4 molar nitric acid. Calculate the pH. All right, so let's see here. We're finally given all the information for our methylamine. So we have 42 milliliters. And again, that is what is in our, for the camera, hopefully I don't drop it. So that is what's in our container on the bottom, and then we're going to titrate our strong acid into this. So what we're doing right now is we're calculating what the methylamine is. Okay, so if you know the volume and the molarity, always start with the volume. Oops, let's put it down here. And what is the concentration? 0.588 moles per liter. So the milliliters cancel, the liters cancel. We're left with moles. And again, when we do titrations, it's all about moles. Okay, we don't care about molarity because we're adding a liquid to a liquid, so it's all about the moles. So what this is saying is we have 0.024, we'll say 7. If you don't want to round that much, that's fine. If you want to keep writing that out. I have 0.024696, but that's fine. And this is moles of my base, or methylamine, whatever you want to call it. And let's see here. Then it says we place 10 milliliters of our nitric acid. And this is a much better problem than yesterday because we have different concentrations, which is 0.4. Oops. And that'll equal something. So 0.004. Now, looking at this information right here, are we at the equivalence point? No. When we're at the equivalence point, we'll have equal number of moles. Okay. Now, somebody yesterday asked, now, Mr. Craig, if you have this many moles of the base and you start adding the acid, won't the number of moles decrease? The answer is yes. But we always want to do this calculation ahead of time so we know how much of the strong to add to the weak. Okay. Obviously, as the titration is going on, when we see the lab, we'll see that progression taking place where this changes, and actually both of these change. But to get to the equivalence point, we need to start with a certain number of moles and finish with the same number of moles of the opposite. Okay, so now that we know how much of our, or how many moles of each, we need to find out the concentration for these, since we did add more liquid to each other. So concentration is moles over liters. Is that 247? And what is my total volume for this? I didn't do that yet. In other words, when I started off with 42 milliliters and then I added 10, and you don't have to show it, but it's going to keep me out of trouble. Okay. So there's 52 milliliters total volume. And again, when we're doing titration, that volume is changing. Therefore, the molarity will change, guaranteed. Okay, so 52 milliliters, divide that by 1,000 equals 0.052 liters. So I get around 0.48 molar, and again, that using the actual number. So did the concentration go down for our base from the original concentration? Yeah, it better. I mean, we have 0.588 moles for 42 milliliters. That's why, because the concentrations are always going to decrease. And then the concentration for our nitric acid, really all we care about is the hydrogen, because we know that's a strong base or a strong acid. We have 0.004 moles. And you can divide that by the total volume, which was 52 milliliters. Okay, so 0.0769. Okay. So again, that's the new stuff. This is titrations. Everything else is the same. Now, we can't use the same ice chart that we had here. Okay, so we can't use the same ice chart because we have hydrogen in our thing here. So we'll have to write a new ice chart. Now we also get to find out a new Ka value. Actually, let's do that first. Unless you want to use the Henderson-Hasselbalch equation. Okay, that's like a curse word in here. That blankety blank Henderson-Hasselbalch. 2.19 times 10 to the negative 10. Okay, and then the ice chart would look like, well, we're definitely going to have hydrogen on the product side. Who's going to go with hydrogen? Is it going to be the base or the CH4OH2? The methylamine. We always put the base with the hydrogen. And then so the, whoop, I just said it, and I wrote something else. And then the conjugate acid is always on the opposite side. Okay. And if you're not 100% sure, then make sure that the number of atoms are the same on both sides. That's probably something you should do anyway, just to make sure that you have the same number of atoms on both sides. Just balancing is a basic skill that we all should have. Our conjugate acid from our previous ice chart had a really small value, like 0.00513. If you want to use that, that's fine. Okay, but approximately 0 is fine, okay, or as well. So we'll put 0.769 in there. And then which of those is smaller? The hydrogen. So the hydrogen is our value for X. And then we'll add it to this side. This goes to 0. And then whatever 0.4 minus that is, right? So 4.4031. Okay, so there's our concentrations. Haven't written an expression yet. So again, products over reactants. You guys run out of room yet? And that was equal to 2.19. So the hydrogen by that, divided by that. Hubbity. I like Mr. Record's new smart board. Has anybody seen that yet? He's having some growing pains with it, but I think I can make it work. Are you just giving me the...
I got 4.2.
Okay. Oh, yeah. Bump it up. All right, so 4.33 times 10 to the negative 11. Oh, Lordy. And then pH would be negative log of that. You guys write small, I hope. 10.36?
Yeah.
Okay. Woo. All right, now, think about this. Does that make sense? What was the pH that we started at? 11.71. We're adding a strong acid, so the pH should go down. Yeah, Debbie.
I got 2.38 and I did the other way.
You're cool. That'll work.
I did.
Yeah, 10.38 is fine enough. Did you do Henderson-Hasselbalch? All right. Yeah, we're good. Equivalence point, what does that mean? Good. And probably a better way to say that is the moles of the weak are equal to the moles of the strong. Now, so what Aubrey said was good, but we want to make sure that we use the correct value here. So which one should we be focusing on? This one right here. Okay. So what that means is we have moles of base, which is actually our weak, is equal to our moles of acid, which are strong. And you'll always have a similar scenario, weak with a strong. Whatever the weak is, that's what we're going to dance with. So we've got 0.247 moles. So at equilibrium, how much HCl do we need? Same number. Good. So knowing that we need that many moles of our strong acid, the question now is, all right, so I know that I have the 0.0247 moles of my base in here. I need to know how much of my acid I need to add to this. Okay? I don't know how much, the volume-wise, to give me that number of moles of acid. So I need to do a calculation to find that out. So knowing that I need 0.0247 moles of HNO3, again, technically speaking, it's still nitric acid in there. I need to find volume, and molarity does have volume in it, so I want to make sure that my moles cancel out, and liters are on top. Whatever my molarity was, I think it was 0.4 over there. Make sure that you put the number with the unit, mole, and then it's per liter, for every liter. So don't get creative and start throwing numbers in there, okay? And I've seen that too many times, and it's disheartening. And then find out how many milliliters, since that's how we'll read our burette. And I think we're going to do the lab Wednesday or Thursday, so depending on when you guys meet. All right, so 0.0247 by 0.4. So 61.75?
Yeah.
Okay. And this is a time that you don't really want to round too much, okay? Because honestly, we can read that closely on the burette. When we do the lab, we'll find out how much we can read that to. And we can actually get that amount. Also, since we know that we have that many moles of the base, what volume was in our beaker initially for our base? 42, right? So our total volume is equal to the 61.75 from our acid plus the 42 from our weak base. So there's our total volume. And again, we start off with that amount in the beaker. Okay, not a pretty titration drawing here. But we started off with 42 in there, and then we added the 61.75 mils here. Okay, so we're adding a liquid to a liquid there. So once we added that amount, now we have a volume of 0.75. 103.75. I don't know what I'd do without a calculator. All right, so knowing that's our total volume, then that's really 0.0 liters. And again, don't round too much at this point. So we need to do what we did back here. Once we know how many moles and our volume and everything, let's find out the new molarities. Okay. And what's really great, at the equivalence point, the moles are the same, right? They should be. Therefore, we really only need to do one calculation for our hydrogen, or our strong acid, as well as our weak base. Okay. These concentrations are going to be the same at the equivalence point. They better be. And the total volume, they're both in the same container. So the number of moles, but don't add the moles together. Don't do that. Over 0.10375. Okay. So 0.238. Is that right? Okay. So we've got our concentration for our strong acid, our weak base. Plug it back into the ice chart that we had. It's kind of melodramatic here. Whoop, not an H. Oop, double R. So 0.238, 0.238. And again, approximately 0, because what we're really doing is we're starting with only the weak base in there, okay? So it's a really small concentration. We'll subtract by the smaller of the two. Well, at the equivalence point, They are the same. So they both go to 0. And then equilibrium is reestablished. Can we use the Henderson-Hasselbalch? No. Don't even think about it. So again, since these are both an unknown, and I'm not going to use X because technically speaking I call that X, but you do what you want. If you're comfortable with it, that's fine. But we'll plug it back into our expression that we use for Ka. So Ka is equal to, actually let's just make it y squared because we're not using 5%, so we don't need to. And again, these are my y's. And you use whatever variable you want. Again, there's no set rule here. And the Ka, 2.19, 10 to the negative 10. So multiply that on both sides. It's 2.19. So 5.12 times 10 to the negative 11, and that's our y squared. So bring the arrow up. So y is equal to 7.22 times 10 to the, is that negative 6? Okay. So, and again, what does y represent that we care about here? The H plus. So, negative log of our hydrogen. 5.14. Okay. And that's at the equivalence point. So we started at 11.71. We added 10 mils of the nitric acid and got it to a pH of something. And then we got it to the equivalence point, and it fell even further to 5.14. Okay?